Welcome back to Ubad's lab, and today I'm going to be explaining related rates using calculus. Alright, I wrote out all the information for this problem that we have here, and I just forgot one thing, 12 feet. Okay, so this is the problem that we have here, and I think this is a pretty good example to work through for related rates, because we're working with two different containers, and this is definitely something you'll see day-to-day in probably chemical engineering or something. It's one container dripping into another container, and we're comparing the rates of change. I definitely think this is a really good example, and if you can do this one, you can definitely work through plenty of other examples. So this is definitely a good one to learn. Alright, so let's first understand what's going on in this example. So we have one cone dripping with it has a certain volume of liquid in it, and that liquid is dripping out into a second container, which is a cylinder, and then that has a certain height of volume of liquid in it as well. And so we're given the height of the first cone is 12 feet, and then we're given the radius of that cone is also is 4 feet, and the height of the liquid in the cone is given by the variable h, and then that liquid is dripping off into this cylinder, and then the height of this liquid in the cylinder is given by the variable y. And then we're just given one piece of information for this one, that the area of the base is 400 pi. And then we're given one more crucial piece of information, which is dH over dt is equal to h minus 12 feet per minute. And this is telling us that the rate of change of h, which is the height of the liquid in the first container, in respect to time, is h minus 12. Okay, so that we'll definitely be using, and it'll definitely come in use. So the question is, when h is equal to 3, what is dy over dt? So when the height of this liquid is 3, then what is the change in the height of the second liquid? So I think the best way to approach this problem would be to figure out dV over dt, which is the change in volume with respect to time, because then that's how we can relate these two containers to each other. That's the only thing they really have in common, since the dV over dt, the change in volume with respect to time, has to be the same for both liquids, except a different sign, because this will be a negative change of volume and this will be a positive change of volume, but the change in volume has to be the same because it's just dripping from one to another. So let's figure out dV over dt for the first container. So let's set up a function for volume. So the V is equal to 1 over 3 pi r squared h. That's for a cone. And now we immediately we can see that we have a problem with this. We have V, we have R, and we have H. We have three different variables that we're working with, and we can't really do this problem with three different variables. So we know that we're going to have to keep the H, because we'll be plugging that in because we're given the value of H is equal to 3. And we're going to be solving for dV over dt, so we have to keep that V for when we differentiate. So we want to get rid of this R. And a way we can do that is by looking at this cone that we have here. And if you look, we have this radius, this height, that makes a right triangle, and this radius, this height, that makes another right triangle. Then we see these are similar triangles, so the ratio of the height to the radius will be the same for these two triangles. So we can take h over r is equal to 12 over 4, which is equal to 3. So we have h over r is equal to 3. And now we want to solve for r, because that's what we're going to be replacing, and put it in terms of h. So let's multiply each side by r, so we get h is equal to 3r. And now if we divide both sides by 3, we get r is equal to h over 3. Alright, so we have r in terms of h now. So let's rewrite this equation with our new way of showing r. So v is equal to 1 over 3 pi h over 3 squared h. So I just replaced r with h over 3. Okay. Now we can rewrite this, which would, it just turns out to be v is equal to pi over 27 h cubed. Then I'm just rewriting, doing arithmetic. I think it'd be a waste of time to work through that. I'm basically just squaring the h, squaring the 3, multiplying that h squared to that h into h cubed, and then multiplying by 1 over 3. In the end, it turns into pi over 27 h cubed. Okay, and now we want to find the change of v, the change in volume. So we have to differentiate using implicit differentiation, since we have these two different variables that we're working with here. So let's differentiate this. We have the v. The derivative of v is dv over dt, and then the derivative of this is you multiply the 3 out, so we get pi over 9 h, and then you minus the, and then you subtract the exponent by 1 squared times dh over dt. Since it's implicit, you multiply by the derivative. Okay, so we have dv over dt is equal to pi over 9 h squared times dh over dt. Okay, and we want to solve in terms of dv over dt, and that's already isolated on the left side, so we don't have to do anything. And now we can start plugging in our values, because if we look here, we have this function that works for all instances of time. We have for when, whatever value h is, and for whatever the change of dh over dt is. But we want to find exactly when h is equal to 3, so we're going to plug in 3 for h, 3 feet for h, and for dh over dt, we know dh over dt is given by h minus 12, which would just be negative 9. So, because we know h is 3, so it'd just be negative 9. Okay, so dv over dt is equal to pi over 9 times 3 feet squared times negative 9 feet per minute. Okay, and if you so the way this simplifies is that we end up just getting negative 9 pi, because if you square this 3, we get 9, and then multiply this out, we get 9 divided by 9, just turns into 1, so, and then it'll be pi times negative 9. So we get dv over dt is equal to negative 9 pi feet per minute. And if we look at this number, whenever you get numbers and you're working with actual applications, you should always look back and see if that number makes sense. Negative 9 pi feet per minute, that's a change in the volume of the liquid in the first container. And this makes complete sense, because if it's a negative value, we're decreasing. And so we're definitely heading in the right direction. Okay, so now let's try to differentiate a function using the second container. So the volume of a cylinder is equal to pi r squared h. Okay, and we know that pi r squared is equal to 400 pi. So so v is equal to, so the area of this base is equal to 400 pi. And pi r squared is the area of the base. So we can just plug in 400 pi right over here. And the h in this one is given by y, so to keep things clear and organized, let's replace this with y, because that's what the problem told us to do. Okay, and now we can differentiate this function. So just to make it clear, this is working with the cone, and this is working with the cylinder. Okay, so we have v is equal to 400 pi times y. Okay, let's differentiate this. Let's find the derivative of both sides. So the derivative of v is dv over dt times 400 pi dy over dt. Okay, we're heading in the right direction because we want dy over dt. That's our final question. So to find, we want to isolate dy over dt because that's what we're looking for. So we can just divide by 400 pi. So dy over dt is equal to dv over dt divided by 400 pi. All right, and now dv over dt, that's all we need now to get this final answer. And what is dv over dt for this second container? I mentioned this in the beginning. It's going to be the same as this one, but with an opposite sign, because all the liquid that exits this container has to enter this container. So the change in the volume has to equal the change in the volume in this one, except with a different sign. So this would be a negative change in volume, positive change in volume, but with equal magnitudes. So we can take dy over dt is equal to dv over dt, which is going to be positive 9 pi over 400 pi. And then we can cancel out the pi's, and we find out that dy over dt is 9 over 400 feet per minute. And that's our final answer. Alright, so I hope this cleared some things up for you. If you're working through some related rates problems. And yeah, don't forget to subscribe and hit the notification bell if you enjoyed the video and to see more stuff like this. Anyways, thanks for watching. I'll see you guys next time.